Is this good? Now, okay. Now we have used conservation of mass, conservation of momentum, and conservation of energy to come up with this equation here. It shows you that if let's say in a flow somewhere, you arbitrarily draw a line. You say, okay, if I know M1, would I know M2? So this relationship shows you that if you know M1, you will know M2, right? So what does that mean? If you simply just look at this equation, you give it an M1, then you will find M2. But interestingly, if you give an M1 that is less than 1, you couldn't find M2. Because M2 will become an imaginary number. Okay? Now, if M1 is equal to 1, as you can see here, if M1 is equal to 1, your denominator, this will be 1. So here will be gamma minus 1. 2 gamma minus parenthesis gamma minus 1 becomes gamma plus 1. And that's a 1, you add it to it. Gamma plus 1 in the numerator. Right? In the numerator of the numerator. So the numerator and the denominator will be the same. So the M2 is equal to 1. So that's a trivial solution. If M1 is less than 1, you couldn't find M2. So so apparently you can possibly find solutions if M1 is greater than 1, right? So from this equation it's probably not very obvious, but we all know that if M1 is less than 1, your denominator becomes negative, right? And your numerator is always positive because 2 over gamma minus 1 is always positive. M1, whatever number there is positive, but your numerator will be negative. So the only possible solution would be for M2 to be less than 1 and M1 greater than 1. Okay, so as I told you, you can just use your spreadsheet to do it. Some of you have done it, right? No one, not raising hand? Okay. So you are not convinced. You should not be convinced at this point, right? If you haven't done it. Or you just simply believe me. That's nice. Okay. As it stands now, believe me, right? Okay, and I'm going to tell you the correct things, but sometimes I make mistakes, right? No one is perfect, so I will make mistakes. But in this case, I think it's pretty much true because I've tested it many times, right? So the only solution would be for M1 greater than 1 and M2 less than 1. So this is kind of interesting, right? You have a one-dimensional flow, and you have a supersonic flow, and somewhere if there's a shock downstream of it, it will be supersonic. Makes sense? And the larger M1 is, the smaller M2 is. So by the time M1 goes to infinity, so M1 has to be greater than 1. But as M1 increases, M2 decreases. As M1 goes to infinity, M2 squared is equal to, when you take the limit, there will be a ratio of this, right? So M2 will be equal to gamma minus 1 over 2 gamma. So M2 will be equal to gamma minus 1 over 2 gamma. So this is what, if gamma is equal to 1.4, what you have is 0.4 over 2.8. So it's equal to 1/7 square root. So your M2 is probably approaching something 0.3 something, right? So 1/7 is what? 1.4? Square root of 1.4 is, cannot be 0.4 but greater than 0.3. Right? So it's about 0.3 something. So M2 will not go to 0, so it's the asymptote. Right? So you probably will find out that if this is M1, this is M2, you have a trivial solution, which is 1 and 1. But only M1 greater than 1, you have solution. Okay? So, how do you do this? When M1 goes to infinity, M2 is equal to 0.14. So M1 goes to infinity. This is another line. How would you draw it? If M1 is equal to 1, M2 is equal to 1. M1 goes to infinity. Apparently, that's not a good way of drawing it, right? Because M2 can never be greater than 1. Why don't we draw it differently, right? So M2, M1, 0. So, because your M2 can only be less than 1, so why don't we draw it like this, right? There's a line here. There's a line here. There's a line here. Now, of course, this is not to the scale. This would be 1 over gamma square root, right? No, I'm sorry. This would be square root of gamma minus 1 over 2 gamma, right? But if we use gamma equal to 1.4, this would be about 0.37 something, right? So you will have something like this. Make sense? Something like that. So really, how of you have used your graphing calculator to do that? Is this what you see? You did, right? Okay. Good. There's a confirmation. So this is roughly what you will see. It's probably also in your textbook. Right? Yeah, probably your textbook. I'm doing the rest of this class.
Loading the numbers. Then 1 being less than 1.
150?
Yeah.
150. Oh, 114. I never did my book.
Usually M1 less than 1. It's negative 1.
Ah.
That's why M1 is subtracted.
But,
M1 less than 1. Yeah. That's right.
here. But then there's a line here, right? That means everything above that cannot be true. Even though it's drawn. Because M1 cannot be less than 1 and M2 greater than 1. You know what I'm saying? So that part of it cannot be true. Mathematically impossible. Right? Mathematically impossible. I mean physically impossible. Thank you. Yeah. And mathematically impossible because so I don't know why that graph was drawn and presented in the text. If I were the author, I would remove it. Okay? If they put in dotted line, you cannot even put in a dotted line because it's square root of a negative number. You cannot draw it on the real axis, x and 1. Right? You can only draw it in an imaginary plane. And since these x, y both are real numbers, you really cannot. There's no way you can draw it. I don't know how they draw it. This is how I would draw. Okay? So that gives you a visual understanding of what the Mach number would be. Okay, so now what is M2? M2 is nothing more than taking a square root, whatever you already have, M1 plus 2 over gamma minus 1, M1 squared. 2 gamma minus 1, and 1 squared. Minus 1. This is in the table, in the textbook. Follow the isentropic table. So you have M1, you have M2. Right, once you find out M1, you will know what M2 is. Otherwise, you just use this equation you can find. Okay? Now, what would be interesting is that your T2 over T1, now across the shock wave, we try to find a relationship between what's upstream or downstream, right? Now remember, the mechanism for shock wave to occur is that a supersonic flow will have to adjust to either a solid surface or back pressure that itself cannot accommodate. So the only way for a supersonic flow to adjust to it is to go through a shock wave, right? So now we are just assuming that if shock wave exists somewhere, M2 and M1, like this, right? So shock wave does not have to exist. For example, the isentropic converging diverging nozzle flow we have no shock wave inside the nozzle, right? But you will have shock wave outside the nozzle. And the reason for that is the flow has to adjust to the back pressure, right? And since it's supersonic, you cannot adjust it gradually, so you have to adjust abruptly. And this abrupt adjustment will occur only within a few mean-free paths of the molecular flow, then you can consider shock wave as infinite infinity. Okay? For the purpose of our work here, we assume the shock wave is a mathematical discontinuity. So it's very thin. It's a so thin that even heat transfer to it makes no sense, right? This is so thin like it's a piece of paper. And you have a supersonic flow coming in, and this is shock wave. You say, oh, where is the heat transfer? You look at the heat transfer through the edge. But since this is so thin, the area is like 0. So there is no heat transfer. So in this context, we are dealing with shock wave as an adiabatic process. It's a compression, very rapid compression, right? And it's adiabatic. And if it's adiabatic, TT1 is equal to TT2, remember? All right, so this is equal to TT2 divided by 1 plus gamma minus 1 over 2, M2 squared divided by TT1. This total pressure upstream and total pressure downstream. This is M1 greater than 1, M2 less than 1, P1, T1, TT1, TT1, T2, T2, PT2, PT2, of course you can say V1 and V2, but you can check it. Right? So this is 1 plus gamma minus 1 over 2 M1 squared. Now remember these two are the same, right? So TT1 equal to TT2, as we said, is an adiabatic process. So thing that you can assume is adiabatic. So this is true. So these two cancel out. So this is the ratio of M2 over M1. So you plug the M2 in here, so it all becomes M1, right? So it's nice to know that once I know the upstream condition, I know everything, right? Because your M2 can also be determined. If this is the case, this becomes, you flip it over 1 plus gamma minus 1 over 2, M1 squared, 1 plus gamma minus 1 over 2, M2 squared. M2 can be a few steps. You plug it in, this will become 1 plus gamma minus 1 over 2, M1 squared, times 2 gamma minus 1, M1 squared minus 1, M1 squared, 2 gamma minus 1, gamma minus 1 over 2, really nice, right? Again, sounds like music because it has nothing but gamma. Right? You have all this. The whole book is filled with symbols. Right? Maybe sometimes you put it back here, to tell you, that's all. Otherwise, it's all gamma. Right? So this is really nice. Now, your momentum equation will give you P2 over P1 equal to 1 plus gamma M1 squared, 1 plus gamma M2 squared. Okay, put it in there, right? So this will become why don't you do this? Do it for yourself, convince yourself. Gamma plus 1 minus gamma minus 1, gamma plus 1. And this is always greater than 1. For example, if you assume M1 is equal to 1, you add these two together, is 1. See? M1 equal to 1, P2 over P1 is equal to 1. Because it's 2 gamma here, right? And minus parenthesis gamma minus 1 becomes gamma plus 1, so it's 1. That means if your number is equal to 1, you definitely will have no shock wave. And since it's a compression, since shock wave is a compression, this has to be greater than 1 as always. In the limiting case, this will be equal to 1. Now, if m is less than 1, this becomes negative. It's like a reverse shock. That's not possible. So instead of flowing going in that direction, you must be talking about flowing going in the other direction, right? But either way, it's fine. Yes?
So is that P or rho?
P. We are talking about pressure. Greater than 1, greater or equal to 1. But if M1 is equal to 1, M2 is equal to 1, there is no shock wave. So some shock wave is very weak, right? Like M1 is equal to 1.01, then your M2 will be like 0.999. Okay? That will be very weak shock wave because as M1 increases, M2 decreases. So you know, a strong shock wave will give you smaller M2, larger P2 over P1, and larger T2 over T1. Now, the trick here is, here we use momentum equation to get P2 over P1, and then we can find out PT2 over PT1, right? So PT2 over PT1 is equal to P2 times 1 plus gamma minus 1 over 2, and 2 squared to the power gamma, gamma minus 1. It's P1 times 1 plus gamma minus 1 over 2, M1 squared to the power gamma, gamma minus 1. Now M2 is equal to, M2 squared is equal to, remember that? M1 squared plus
2
plus gamma of 2 over gamma minus 1, 2 gamma, gamma minus 1, and 1 squared minus 1. Plug it in there. A lot of algebraic operations, right? So, a simple way to do that is to put 3 dots, right? And then, this becomes gamma plus 1 over 2 and 1 squared, 1 plus gamma minus 1 over 2 and 1 squared to the power of gamma, gamma minus 1, 1 over 2 gamma, gamma plus 1, and 1 squared minus gamma minus 1 gamma plus 1 to the power 1 over gamma minus 1. So here, the PT2 over PT1 is really derived from the fact that you know P1 over P2. This is kind of different from the temperature, right? in temperature relationship, because we know that TT2 is equal to TT1, so we derive T2 over T1. But for pressure, it's just the reverse, because we know P2 over P1 from the momentum equation, we derive PT2 over PT1. Now, this is always less than 1. Always. Because when 1 is greater than 1. So this is what we call PT2 minus PT1 is equal to pressure loss. Because PT2, oh no, I'm sorry, PT2, oh, you can call it that way, is less than 0, right? So you can, because it's negative, so we call it pressure loss. So this is pretty interesting now. So what's really happening here? You are just operating all this mathematical equation, and you come and say, hey, there's a pressure loss. How do you understand it physically? Because if you just follow these equations, you say, oh, these are mathematics, right? For example, we say, oh, 2 is greater than 1. You say, who says? Right? Who said? Who defined 2 is greater than 1? Or 3 is greater than 2? You ever thought about that? And these are kind of like that too, right? But in mathematics, when you say 2 is greater than 1, that's you define, right? You see 1 plus is equal to 1, you see 2 equal to 2, so 2 greater than 1. Physics, right there, right? Reality. You just name it as 1 or 2, right? For example, say 1, 2, 3, 4. You can rename everything 9, 8, 7. It doesn't matter as long as you define it, right? Now, here, because we define the pressure PT2 as the downstream stagnation pressure and PT1 as the upstream stagnation pressure, and when you do the mathematical operation, this turned out to be less than 0. So what happened there? What happened there is really without detail manipulation. That's what I'm saying, okay? S2 minus S1 over R is equal to minus log PT2 over PT1. So PT2 over PT1 is really equal to the exponential function of minus S2 minus S1 over R. Sharp S2 greater than S1. Therefore, PT2 over PT1 less than 1. So physically, what happened is that you have a very abrupt compression of the gas by the shock wave. And you remember in thermodynamics, we talk about if the compression or any process that occurs too abruptly, the entropy increase tends to be large. And so in a fluid flow, shock wave probably is the most non-isentropic process you would encounter. Okay. So your S2 over S1 will be much larger. S2 will be much larger than S1. So physically, this is really what happened. It's the entropy. Okay. So what does that mean? Your PT2 being less than PT1 means that if you have a shock wave, your gas really, or your air in aerodynamics, really loses its ability to expand. Right? Let's say if you have a shock wave which causes PT1 to go from 500 kilopascal down to 200 kilopascal in terms of stagnation pressure. Now, stagnation pressure means what? It's actually the maximum pressure you can see in that flow. Remember, stagnation pressure is whatever you already have. You bring it isentropically, nicely, slowly, down to zero velocity. That's the pressure you can get. Even if you do it isentropically, that's the maximum pressure you can get. So, if you think about it reversely, in the other direction is the expansion. So, if your stagnation pressure is already down from 500 kilopascal to 200 kilopascal, that means downstream of the shock wave, your gas cannot expand as if you can go from 500, let's say, to 100. Now it can only go from 200 to 100. Right? So it cannot expand very much. That's why you don't want to have shock wave, especially in your propulsion device, or in your combustor, or in your rocket chamber. You definitely don't want to have shock wave. Okay? Because it loses the power to expand. And if it loses the capability to expand, that means the flow velocity cannot be very high. Right? That means you also lose the momentum. Yes.
Which one's slowing up just a little bit? I have a question about the equation. Yeah, on the top right of that paper, it's like kind of scribbly term. What is that? Yes.
Two, yeah.
And then would you mind explaining a bit more about how that stagnation pressure changes and why it's that thing? I don't fully understand that concept.
Anyone can help?
You generated entropy, which means you're wasting energy, adding disorder to the system.
So a high pressure change between PT2 and PT1 yields less overall thrust within an engine that creates a shock.
It's not isentropic.
The shock creates this, not the other way around. You have a process. You think of shock wave as a compression process. Do you want to be compressed nicely, slowly, or you want to be compressed abruptly? Yeah, I like that too. See, this is a bad example. Yeah, I don't advocate this, but just for the sake of explanation. If someone snaps on you, and you have sponge, this thing, not much here, right? There is no sponge. You immediately experience entropy increase very sharply, right? You either knock the air out of you or cause all this spinning stars. Right? And after that, you lose capability to recognize or think or do any work. You cannot do that way. Alright?
Thank you. That definitely helps.
So entropy increase is always not very true. Yes.
Probably a dumb question, but the P2 over P1 will increase, but PT2 over PT1 will decrease.
Exactly. Okay, so this is the part that is kind of, so the question is that across the shock wave, PT2 over PT1 actually becomes less than 1, but P2 over P1 becomes more than 1. You say, well, how can that be, right? Now remember, PT is kind of the ability to do work, right? You imagine if you have a high pressure reservoir, high pressure gas in there, you can do a lot of work. Why is it? You go to tire place, you change tire, you inflate your tire. There's a reservoir, right? If that reservoir is under high pressure, even given the same volume, you can inflate more tires than if the reservoir is not at such a high pressure, right? So the high pressure reservoir, even given the same volume, can do more work. So one example I gave you earlier in the semester is that if someone built an air reservoir in your neighborhood with 3,000 psi, your property value drops like a rock, right? Because it's dangerous. That means if something happens, it can do a lot of work, but in this case, damage, right? In the form of damage, right? So, when you go through a non-isentropic process, you always lose ability to do work. One thing you can also do, for example, today after work, if you drive back to your place, you step on the gas, get it to, let's say, speed limit. Okay, don't over speed. Get it to speed limit, and then you release the gas. Don't do anything. Your car slows down, right? Why is it? Friction, right? And friction is irreversible, right? Frictional process is irreversible process. And if you have irreversibility, your entropy increases. So every day you are increasing the entropy in the universe. Every day, everyone, including me. No matter what you do, you are increasing the entropy. And because you increase the entropy, in the example of your car, it loses the ability to go, right? It just eventually slows down. Of course, you have an idle RPM about 800, so you're still chugging along. But if you just turn off the engine right there, it will eventually stop. Right? Because the friction, the irreversible things happening all the way eventually kill its ability to move. Right? That's why you keep pumping in gas, just to keep it moving. Right? And here is kind of similar. If you don't compress the gas or do the work to re-energize the gas downstream of the shock wave, the gas downstream of the shock wave just loses part of its ability to work. Okay. So this is very important. That's why we call it pressure loss. So the pressure loss is not about P2. Right? Earlier I also said the pressure loss is about the loss of ability to expand. So your expansion ratio will become low, right? Because let's say you are expanding the gas into the ambient, and because of the shock wave, your stagnation pressure goes down from 500 kilopascal to 200 kilopascal. Your expansion ratio can at most be a factor of 2. Now, if you have 500 kilopascal, it will be almost a factor of 5, right? Because ambient pressure is about 101.3 kilopascal. So when you